Okay, so we're going to talk a little bit about Chapter 8. Chapter 8 is really beginning of organic. In a sense, we have all the background we need. Now we're going to talk about reactions. And that's what the organic chemistry is, reaction. So we're going to start with a little introduction. Then we basically go and let you to read the organic chemistry in nature or I'm sorry, alkene. Might mention that later on, but at this point, I'm going to concentrate more on naming and different addition reactions. So addition reactions to double bond that includes many topics is really the key of the focus for chapter 8. So let me put something, change my little paper here and put my naming on. So naming again is very similar to what we learned in alkane. So we have to number the carbon. So we start with the lowest number to the highest number that include the longest chain. Now the difference is in this scenario we have to include the double bond. Double bond always get 1 and 2. So whenever we start we have a carbon number 1 and carbon number 2. That is a double bond or alkene. So if you look at this, we have 7 carbons. So the 7 carbons has a substitution, a propyl substitution, and of course, like other naming, we have to name the substitution first. So substitution is a propyl group because it has 3 carbons. So this becomes 3 propyl, 1 because the position of double bond, which is the En, is number 1. Or we can name it as 3-propyl. It's a new naming. Hept means we have 7 carbon. Again, we identify where the double bond is 1. Then we're going to put the Ene in there. So that means the double bond is on carbon number 1. Now let's talk a little bit about E and Z. Remember we also had E and Z in the previous chapter, and cis and trans. So we need to go back and look at the priority we learned in RNS. So this priority system we learn in RNS system. So if the double bond, so we draw a little line here. Now if the double bond is 1 and 2, we only have 2 bonds to consider. So my suggestion is always to look at left and then look at the right. If I look at the left of this molecule, this bond here, if it has higher priority than this bond, so I really use a chevron. You can also use other things. So my chevron says this bond here higher priority than this bond. The same thing here. This bond has higher priority than this bond. So the priorities are the same. So this is not a cis or trans. We're going to call it a Z. The Z comes from German, zusammen, means together. So together. Now, if the priority is a little bit different, if you have a 1 and 2 here, but change it here, 1, 2, so the priorities are a little bit different from each other. So that would be intaken, the opposite in German. So this would be E isomer, and this would be Z isomer. So if I go back to the example, so we have the double bond here. We draw the line between the two. Look at the left side. The left side, this bond has higher priority than this bond. So it has a higher priority than the other bond. So let me use a different color to show that priority. So we have a priority. Oh, I have a little thing here. So it's higher priority than this. And the other one is opposite. Priority is higher for the bond here than this one. Because the priorities are different, so this would be an E isomer. We only have one double bond, so we put that E here. So this is the E, indicating that the double bond has an E configuration. Then we go name it as before, so we need to do the longest chain. So the longest chain is basically 8 carbon. And we put the substitution first, which is 4 and 5. We have 2 ethyl groups, diethyl. We have 3 methyl groups, 2, 2, 7, trimethyl. 4 indicates where the ene is, right? 4 indicates where the double bond is. 4 ene. So that would be their name. So again, if the double bond has an E and Z configuration, we need to indicate that in our naming. Okay, so back to a little bit more example of E and Z to review ourselves for that. So if I look at this molecule on the top, so we can see on the left side, we have a carbon OH. Again, the double bond is our attention. So we have 2 carbon which are connected to the double bond. This carbon has a OH and this carbon has, sorry, C double bond H. So if you recall C double bond OH, we counted O twice, has a higher priority than OH. So this would be 1 and a 2. So this would be a 2 and a 1 because again, carbon-carbon double bond we count twice. We count that twice. So that's higher priority. Now these two are opposite to each other. So again, I drew it here. 2 and a 1, 1 and a 2. So they're opposite to each other. So this would be a not zusammen, they're not together. They're opposite antagon E isomer. So let's look at what I drew back here. So we have 2 carbons. We have a methyl group, and we have 1, 2, 3, 4 butyl group. Again, the number of carbons is important. So this would be priority 1, priority 2. Here is the opposite. We have a H. Remember, typically when we drawing these isomers, when drawing this double bond, we don't show the H. So we don't show the H, but we should be aware of the H. Even though H is not shown in this structure, we have to remember that there is a H there, and that is going to help us to identify E or Z. So now this structure I drew, also they're opposite to each other. So this also would be E isomer. So we have 2 E isomers here. So now let's look at the English name and how we're going to identify E or Z isomer. Very simple, actually. So my suggestion is at the beginning, go a little bit slow. Draw the carbons. So we have hipped. So that means we have 7 carbons. So I drew this 7 carbon. Then I look at this 3. So I say the 3 basically tell me that the double bond is at carbon number 3. So I drew it here. So I put a double bond between 3 and 4. Remember, the lower number gets the ene. Then I went and looked at this methyl group here. So we have a substitution, position 4 and position 5. So at position 4 and position 5, I put my 2 methyl groups here. Now we're going to pay attention to the double bond to make it E or Z. Remember, we have to make this an E isomer. So again, I look at the double bond. We look at the double bond, and we realize that carbon number 3 and carbon number 4 are the one that makes this molecule E or Z. So my suggestion is always draw a line between the double bond and only work on one side of the molecule, not both at the same time, till you feel comfortable. So if I look at the left side, I can put CH3, CH2. Remember CH3, CH2 here, and put the H here. So this tells me now on the left side, this has higher priority than this one. So the priority on this molecule, if I use a different color, again is 1, and this is 2. So my chevron is like this, higher, higher. Now I want this on the left side, I want to be the opposite. Remember, we wanted this to be a E isomers. So again, I put the methyl group here and CH3, CH2, CH3 here. So now my priority is different. So this is a priority 1, and this is priority 2. So they're now the opposite to each other. And this would be an E isomers. Now again, this is a typewriter structure sort of. So if I want to draw a zigzag structure, I have 1, 2, 3, 4, 5. I'm sorry, 1, 2, 3, 4, 5, 6, 7. So I can draw it. And remember, again, the H in a zigzag structure are not shown, but again, it's understood. This is a E isomers. This is a E isomer. So you really do a little bit practice from homework B. We have some of this in homework B, something in the C, and etc. So we need to practice. Okay, so let's talk a little bit about the cyclic structure. Cyclic structure a little bit different, but the same rule. So we start again 1 and 2. Always a double bond. Remember, 1 and 2, 3, 4, 5. You go around. So this is a cyclopentene. Now, if he has a substitution on it, like here, if I put a methyl group here, so this methyl group, it's symmetrical. It doesn't matter. I can count. We have to count 1, 2. 1, 2, 3, 4. So methyl group is position 4. Now, if I put 1, 2, 3, 4, it would be the same. But sometimes it doesn't work that way, like the case would be here. So we have 1, 2, 3, 4, 5. Now, if I number it the other way, 1, 2, 3, 4, 5, this methyl group gets a higher number than here. So that's numbering is not right. So we have to start 1, 2 as such to give a lower number to this first substitution. That's the same rule you had in alkane. Same. Okay, now here's the major part of this chapter. So in this chapter, we're learning many reactions. What's the best way to learn it? Just practice. I don't know any other way to do this without practicing. So what do you usually start with? The starting material? So starting material, we called it a 0. So this is my 0 starting material. Now, I have many products from this reaction. So we start with methyl cyclohexene. Methyl cyclohexene. We have a methyl group. We have a H. Or attention has to be on the double bond. So this is what we're learning today is the reaction of double bond. So if I have a double bond here, and look at that, the double bond, it basically is gone in all this product. So we have 10 different products. So the key to remember a couple things. We start with the starting material. We have 2. We have a double bond. We look at the product. Again, we look at the starting material, we look at the product, and see what has been added. So we look at this and look at this. We added a BR and a H. Now there's a rule we're going to talk about in more mechanism way, but at this point, just simple. The H, I call it, is added. This H in the red was added to this carbon that has a H. So basically, when we add H and a BR, and a H was added to the carbon that had already an H or more H, That's what we call Dr. Markovnikov rules. So Markovnikov rules, as I call it, is we add the H to a carbon that already has more H's. So between these two carbons, this carbon doesn't have any H, but this carbon has one H. So we add the H here. So that's rule number 1 for Dr. M. So we add H and a Br to these two carbons. We add the H to the carbon that has already an H, or more H, and the Br goes to the other one. Now, look at this one now. We talk about that. We add H and a Br. We add a H and a Br to the double bond, but is the opposite. H is added to the carbon that doesn't have an H. So usually, to make this simple, I'll call this Dr. M, and we follow it, draw a line through it. So it means that this addition of H and a Br did not follow Dr. M. So we're going to learn that. Now we are already just adding and looking at these reactions and changes, but we don't have a reagent here. So we need to learn what reagent do we have to add H and a Br, either following Dr. Markovnikov or not following Dr. Markovnikov. So we have to learn all these. We have to learn the reagent. We have to learn what those reagents add to the double bond. It takes practice. Now, if I look at number 0, it's a little bit faint here. Number 3. So number 3, basically we add H and OH and also follow Dr. Markovnikov. We add H to the carbon that already has more H's, and we add OH now to this carbon. We also say this follows Dr. M. So Dr. M follows here. Now we look at the other one. So we add again for carbon product number 4. We add H and OH, but it's different one from 3. We add H and OH opposite to Dr. M. So this didn't follow Dr. M. So Dr. M was not followed, but we add H and OH. At this point, we're also looking at the stereochemistry. We didn't look at the stereochemistry for the first 3. We can see that H and OH are added on the same side of the molecule and kicked H, this H, OH was added here, H, and a methyl group coming toward us. Now, we don't make that exclusively, we make both of them. So we make not only this, we also make the enantiomer of this compound. So it's a mixture of the two, which you remember is called racemic mixture. But this reaction from 0 to 4, is stereoselective. So we add H and OH on the same side of the cyclohexane ring and kick the methyl group and H toward us. We add H and OH, stereoselective. Now, what if we add a hydrogen gas? We're talking about reagent. So if I add a hydrogen gas to this double bond, I add H and a H, and both these H's are coming from the bottom or the top. Again, it's stereoselective. And we make the enantiomers of this. So we add H and a H for this reaction. Reaction 0 to 5, we call it. Then we're looking at reaction number 6. So reaction number 6, we add Br and a Br, and these two Br are opposite to each other. So one of the Br is coming toward us, one Br is going away from us. So there's no Dr. M here or here because we're adding the same thing, H and H, Br and a Br. Now the next reaction, reaction number 7, is a little bit different. We add a mixture of, basically if I talk about it right now, bromine and water. We add a OH and a Br. and Br is added always here. Now, how would I know that? How would I know that? So when I teach this part, I tell the student, think about Br as a H, even though it's not H, but Br adds to the carbon that has more H's. That's how I remember. So we added Br and an OH. Again, stereoselective. Br coming toward us, OH going away from us. The way I drew this now still makes the other one, the enantiomers. Not exclusively this one, but we add OH and a Br. Here now from 0, I call this one HA and HB. So I broke it down to 2 sections. So we add a reagent that we're going to talk about it. That what we made, this O is attached to both carbons. So this O attached to the carbon is an epoxide, which is in one of the glue we use, epoxide glue. Now this epoxide, O attached to the 2 carbon, is not very stable. We can add a reagent to it to make it into OH and OH. We break it up. Now again, if you look at it, these OHs are opposite to each other. Opposite to each other. But these opposite to each other that we learn, we call that anti-addition. Anti-addition means the 2 OHs, in this case, are opposite to each other. So far so good. Many reactions. We need to practice. Here now we have a 0 again to number 9. So if I look at 0 and 9, the difference between the 2 is we added 2 OHs. But interesting enough, this reagent provides us with the OHs at the same side. So if you look at, we have an OH here and an OH here, and I drew a such that they're away from us and kick the methyl group and H toward us. And of course, we have the other enantiomers. So there's a difference between reaction 0 to 8B and 0 to 9 because of the location and the way we added. So we added all at the same side. These are called syn addition versus the anti-addition. So syn addition means they are on the same side. The last but not the least is the 10. So we're going to talk about that a little bit later on. 10 is actually the only reagent that we have that breaks the double bond. Other ones, the double bond was gone, but the cyclohexane stays behind. Here, cyclohexane doesn't exist anymore. But we still have 6 carbon. So that doesn't change. So if you count, we have 1, 2, 3, 4, 5, 6, 7, because remember there's a methyl group here. So you have the 6 and 1 here, 7. So methyl group is this corner. 1, 2, 3, 4, 5, 6, 7. So we count the number of carbons for this. Okay, we're back with slide number 7. Wow, many reagents. But we have to practice. We have to practice. So we look at the 0 to 1. So 0 to 1, if you recall, we add H and a Br. So the reagent or combination reagent for this reaction is HBr when we add HBr to the double bond, but there is no peroxide. I mean, there's a little story behind it. Then we have, remember HBr that didn't add Dr. M. So this was follow Dr. M here. Dr. M was H goes where there are more H's. This one did not follow Dr. M. So when we do, we add it, it's still HBr, a little bit peroxide. And we're going to talk about mechanism for this later on. So this one is a little bit complicated, or too many things I wrote here. So we add H and OH, so we can use basically water and acid. So if I use water and acid, only water and acid. So that add H and a Br and follows Dr. M. The other way to do that, and we're going to talk about that in more details, is mercury acetate water, and a sodium borohydride. So we have two set of reagents for this part. So either of these, mercury acetate and water sodium borohydride, we add stepwise, adds OH and AH following Dr. M. So this follows Dr. M. Then we add boron. So again, two-step reaction. So you add boron, BH3. It's not easy to read it in my handwriting. BH3 and sodium hydroxide. Add H and OH, and it does not follow Dr. M. Does not follow Dr. M. For the other reaction to number 5, we add hydrogen gas. I think I mentioned that. Hydrogen gas and palladium as a metal. So it doesn't matter if you use Dr. M or not, but it's enantiomers. Remember, we make different isomers. Bromine, if we add bromine to the double bond, we add 2 BRs. Again, it's stereoselective. If I add water to the bromine, we add H and OH. Remember OH and H? I'm sorry, bromine and water, we add, said the wrong thing, OH and a BR, and BR act like H. Sorry, I made a mistake. Now, for the epoxide, we talk about epoxide, we add acidic, some kind of per acid, not acetic acid, per acetic acid to make epoxide. We're going to talk about that. Now, the epoxide react with acid and water to open up, to make two OHs, to go from a basically a alkene to OHs that are the same side. Remember, this is a syn addition. What a new reagent we haven't seen before is osmium. OS is osmium. Osmium tetroxide, oxidizing osmium, and then we reduce it with sodium bisulfite. Two set of reagent. Now this one to a aldehyde ketone, we're going to talk in more details later on. We need to use ozone, and the ozone follows by dimethyl sulfide to make number 10, which is a combination of aldehyde and ketone for this alkene. So I'm going to stop and then have a different YouTube, got long, for some exercise we can do together. Thank you for listening.